Okay, so now that we've gone through the exam, let me go through some quick announcements. So I've got, after today, I'm going to take the attendance, and I've got to update the attendance not only from today, but I don't think I uploaded last Thursday's attendance, so I'm going to do that all at once. But let's take care of some housekeeping. So first off, in terms of exams, no more exams until the end, until the final. So unless you'd like another one. Oh, no, okay. Now we've got some response. So just so everybody's clear on the calendar, so we have today we're going to be talking about analysis of stress and stress transformations. Just so you're aware, stress analysis and Moore's circle, they kind of bleed together. It's all sort of one big topic. What we're going to do on Thursday, November 15th is between today and next time, I'm going to basically lay the foundation for everything that's needed for stress transformation. And combined loading is just going to be some really, really simple example problems. The nice thing about this science is once you boil it down and actually get right down to stress transformation and stresses on inclined planes, it's actually really simple. I will go ahead and warn you that the derivation to get there, I'm going to throw some trig at you like nobody's business. Okay, so there's going to be a lot of trig thrown at you today, and a lot of those trig identities that you forgot, like the sine squared equals 1 minus the cosine squared and all that stuff. I'm throwing a lot of that at you today. But it's going to feel a little bit like movie time. So you can follow along and write down the derivation if you want. I'm not going to make you reproduce it. I really just want to make sure that you're following along. Keep in mind, all these slides are available on Blackboard. Now, in terms of homework, you all have a homework due on Tuesday on beam deflections. Now, we've already covered all of the material, so I thought I would open it up to see if anybody had any questions about the homework assignment that's due on Tuesday. And they're like, oh, I forgot we had a homework assignment due on Tuesday. You do? Yes. Okay, I'm just kidding. Yeah, go right ahead. So this problem, you have a simply supported beam with a concentrated moment applied at A. And what were we trying to determine? Maximum deflection? Yeah. Okay. Let me see your moment function. Okay. Here's a good idea for this problem. Just as a way of making your life a little easier. Unless, I don't know, did the book actually locate the coordinate system for you? Did it say, here's where your axes are? Yeah. It did? Yeah, it does. Okay, never mind. It does have the line, the part right there. Here's what I will do for that problem. What I will do is I will go back through the solution guide, and if I have determined that it's just too involved algebraically, I might throw some numbers at you and say, just assume these values. Okay, but don't quote me on that because I want to see it, because there is also a possibility that it's just, an algebra error. The reason why I say that is this. The moment diagram on that problem is a line. It's a y equals mx plus b, which it looks like that's what you've got. Well, conceptually, that should be simpler than what we've done in class where we've had parabolas. So it should be a lot easier to reconcile where max deflection is. It should. So if not, then, I know you're not going to like this answer, but you might want to just break out some scratch paper and almost like start it again to make sure that you're getting the algebra right. I don't really have much guidance other than that. I know the calculus is right, but yeah, okay. Remember that your boundary conditions are both at x equals, or x equals 0 and x equals L, that your deflections are 0. So, but I don't really have much of an answer. I know that sucks, but. Any other questions? I will look at that, and if the algebra really is too involved, I'll throw some numbers at you to make it a little easier. Sound good? If you want, what you can do, this is something you can do that make your life a little easier. Take the length of the beam and set it equal to 100 feet. There's a reason why I pick 100, okay? Because if you're throwing a number in for L, it's probably going to make it easier to actually come up with a numerical value for X, okay? So let's say you use 100 feet and then your X value comes out to be like 62.6. Well, then you could extrapolate and say, well, X is 0.62 whatever L. Does that make sense? So if it makes it easier for you algebraically, assume that L is 100. There's nothing wrong with that. So. All right. Is that good? All right, try that and let's see. Are there any other questions? All right. Okay. Like I said, today is going to be a little bit like movie time. So yeah. Just bear with me, okay? Now, as we mentioned last time, remember, you've got your karate chop, you got your judo chop, you got your ninja chop. Don't go karate chopping while you're kung fu kicking. Go like that. There goes your leg. It's an old video. Look it up on YouTube. Look up West Virginia Ninja. You can't miss it. What's that? I don't remember. It was? Is this a can of skull? No, says I. Get it right about like that. In the Ninja Star. Never thought you would bring that up in a technical engineering course, right? Oh, I know. There's some student out there at some school in like Indiana going, what? Just look it up on YouTube. Okay, what I'm getting at, and I'm being a little silly, but what I'm really getting at is we haven't really tackled the topic of orientation. And what I mean by that is, here's a problem. We have a beam, we cut a section, and we look at shears and moments and deflections and all sorts of, all sorts of stuff. But when we cut our section, we've sort of had an unwritten rule up until now that if the beam is going left to right, that we would cut our section up and down, okay? Well, my question is this. What if we cut our section at an angle? What if we inclined our stresses, okay? Now, it stands to reason that we would get different stresses on a section like that, okay? Now, here's the thing, okay? I'm sure that you're probably like, Dr. Mike, why are you making this more complicated? Who cares? Like, just keep it simple. Well, I can understand that. And this is probably one of the points in the class where I am going to complicate it a bit. But there is a very specific reason, okay? The reason why we're doing this type of analysis is because I want to try and help you understand what's the worst case scenario for elements that are subjected to multiple stresses. And this is valuable for both you civil engineers and you mechanical engineers in the room. For you mechanical engineers, if you have a camshaft that's being twisted and heated up and bent and sheared and all sorts of different stresses, or even if it's a structure in an element in a building, if it's an element that's being sheared and pressed on and bent, there's going to be different stresses for different locations. So, we've been handling these problems one at a time up until now. If you have a circular shaft that's twisted, you all know how to determine the response, the shear stresses, the angle of twist, and all that. If you have a member that's being yanked on, you know how to determine the axial stress, the strain, how much it's going to deflect and whatnot. But how do you handle it if it's got both on it? How do you handle it if there are multiple loads and multiple stresses? That's sort of where this is going. Okay, so I just want you to be aware of that. Okay, now let's start off with a simple case because I want to illustrate what I'm doing. Okay, so note I've got these X and Y axes there, so just bear with me. And I'm going to keep it simple. Let's say we have a single member subjected to a single axial load P, and I'm yanking on it. If we cut a section perpendicular, right, look at a little slice. I got P going this way. I have a normal force in that section, which is P going in the opposite direction. So I can determine the stress very easily. I propose that on this section, the normal stress is going to be P over A, right? Now, on this section, if the normal stress is P over A, what's the shear stress? It's not a trick question. You can just look at the diagram. How much shear stress is on this section? Like, how much am I doing this? Zero. There is no shear stress. So for this section, or for this orientation, the normal stress is P over A. The shear stress is 0. Okay? What if I do this? What if I cut a section at an angle? Okay? Well, by cutting a section at an angle, I propose that you're going to develop some amount of normal stress and some amount of an inclined shear stress V. Now, I've got these stresses shown, or these resultants shown in positive directions just to keep the math simple, but I want you to recognize that we are going to have moments and or normal forces and shear forces. Keep in mind that these are going to be a function of the angle theta, whatever our angle is. Are we cutting like this, or are we cutting like that? Whatever that angle is going to change what our resulting stresses are and whatnot. Now, we can use some basic trig to determine the components of each of these. So if you have a normal force at some angle, the y component is in sine theta, the x component is in cosine theta. Now, here, if you notice, this isn't a typo. Like, see how here the x component is the cosine, but over here the x component is the sine? It's because your angle's measured off the other axis. Remember, if you're drawing a line and you have an angle, right, the sine of that angle is equal to the cosine of 90 minus that angle. Remember that from trig? So when you're flipping your force component, you're flipping your trig functions as well. Okay? So that's not a so that right there, that is not a typo. That's intended. Okay? So if you're okay with that, and again, if you all want me to stop and hold off and say, Dr. Mike, my hand is developing some significant stress right now. No pun intended. And you need me to stop, let me know. Now, if I've got, so if I go back to this and I got x component forces and I got y component forces, I can break out my old familiar sum of forces in the x direction and my sum of forces in the y direction to result in two equations and two unknowns. So I've got n times the cosine of theta minus v times the sine of theta equals p. How did I get that? Well, everything going to the left has got to equal everything going to the right. So I've got p going to the left, and I got v sine theta going to the left, and to the right, I have n cosine theta. So sum that up, and I have this equation. And then over here on the right, I've got everything going up. Has got to equal everything going down. Well, I don't have anything going down. All I have is n sine theta, and I have v cosine theta going up. So add those up, and that has to be 0. So I got this whole two equations and two unknowns scenario, and I have to use these two equations to solve for my unknowns. My unknowns being the normal force N and the shear force V. Okay? You want me to leave this up here for a second? Or? Okay. All right. So what I am not going to do is go through the algebra craziness of solving for these. Trust me that taking this and solving for N and V, you get that. If you don't believe me, you can go through the algebra and check it yourself. Just remember, you're going to have a lot of trig identities pop up, and I'm not really worried about that for here. Now, it's really easy to verify if what I'm doing here is correct. What if your angle is 0? Remember, your angle is the angle of inclination of your cut. If the angle is 0, we're making a perpendicular cut. Now, if the angle is 0, what is N? Well, it's P times the cosine of 0, which is just P. V is negative P times the sine of theta, and that's 0. That's what we said earlier. If we're cutting like this, we got a normal force of P and a shear force of 0. Okay? Everybody all right with that? That's not, I don't think that should be incredibly complicated. Okay? So, if you understand that, we need to determine stresses. Remember, in this course, we don't really care so much about forces. That was statics. What we need is to take those forces and resolve them into appropriate stress components. Now, we're going to be using our fundamental definitions for normal stress and shear stress, which is a force applied over a given area. The only thing to keep in mind is that your shear area changes. Remember, if you're cutting a section like this, then the area is just A. Well, if you're cutting a section like this, your area isn't A. It changes a bit. Specifically, it's the area divided by the cosine. Because think, imagine if you had, a stick of butter, since we were talking about butter earlier, right? And imagine if you cut the butter like this versus cutting the butter like this. The area is bigger, right? If you cut like that, like that's a bigger rectangle, right? So the area is going to be different, and you have to account for that appropriately. So we're going to call that A sub t, call it, the tangent area or whatnot. Okay? Now, before we start breaking out and computing our stress calculations, I got to throw some notation out at you. Okay? And this is something you haven't seen yet, so I'll take my time on this. Okay? Now, if you go to your book, personally, I think your book makes this a little more complicated than it needs to be, because what your book uses is x and y for your original coordinate system, and then x prime, y prime for your new coordinate system. And so you got x's and primes and y's and, lions and tigers and bears all over the place. And I think it's a little more complicated to follow. What I like to use is x and y for my original coordinate system and 1 and 2 for my new coordinate system, because I think it's a little easier to follow. Okay? So to give you kind of an idea of the notation, okay, if I say sigma sub x, okay, what I'm saying is normal stresses, and I'm talking about normal stresses normal to this axis, this x-axis, normal stresses this way, okay? If I'm saying sigma sub 1, I'm talking about normal stresses, but I'm talking about normal stresses this way, okay? Is everybody okay with that? Ultimately, what we're going to be computing or deriving are some relationships related to what's called stress transformation. In other words, if you have a stress this way, how does that transform into a stress this way? That's going to be sort of a focus of what we're doing. Now, for shear stress, the notation is going to be something like tau, let's say 1, 2. So if I say tau 1, 2, what I'm saying is that shear stress is perpendicular to the 1 axis and it's parallel to the 2 axis. So my surface is perpendicular to the first axis and the stress is parallel to the second axis. I'm a little loosey-goosey on that because when we start deriving, you're going to see something kind of interesting about your shear stresses pop up later. So I'll save that for later. Okay, everybody okay with my notation? Everybody fine with that? Okay, so here's what I propose, okay? So this is what we computed earlier. This is my normal force and this is my shear force, okay? So I want to digest this slide a little bit. This slide takes a little bit of digestion, okay? So first off, let's look at these 3 equations over here on the right. So I have sigma x is P over A, okay? First off, why am I calling it P over A? Remember, let's look at our areas. The area of this plane right here, remember this is like 3 dimensions. This is going to come out of the screen. The area of this plane is A naught. The area of this plane is A divided by the cosine, okay? So P over this area is a stress, and I'm calling it sigma sub x because it's along the x-axis. It's stressed this way, okay? Sigma sub 1 is stressed this way along that new coordinate system, and that new coordinate system is defined by that angle, okay? Now, how am I computing that? Well, I'm taking n, dividing it by that transverse area, or that tangent area, okay? So do you see how I'm getting sigma x is P over A, the sigma 1 is n over AT? Everybody okay with that? Tau 1, 2 is V over AT, okay? Tau 1, 2, okay? Here we go. So think about what that means. Tau 1, 2. It's perpendicular to this axis number 1. It's parallel to this axis number 2. Everybody okay with that? All right. Now, let's take these expressions, and again, if you need me to hang out here, I'm more than happy to. Let's take these expressions and let's see if we can make them more complicated. Now, what am I'm trying not to make them complicated. I'm trying to make them simple. Okay? How am I making them simple? Well, I'm going to use what's in those blue boxes. Okay? Let's take a look at those blue boxes. This is what I was talking about earlier. I'm going to start throwing out some trig identities that you haven't seen in, forever, right? So, for instance, that one on the right, like what is the sine of 2 theta? It's 2 times the sine of theta times the cosine of theta, right? Sine of 2 theta is 2 sine theta cosine theta. So if I solve for sine theta cosine theta, I get this, sine of 2 theta over 2. Okay? Also, what about your cosine squared and your cosine, or your cosine squared and your sine squared? Well, if you remember, cosine squared is 1 plus the cosine of 2 theta over 2, and then sine squared is 1 minus the cosine of 2 theta over 2. Okay? What you're going to be seeing are a lot of double angle formulas, a lot of 2 thetas. And there's actually like a mechanical and physical reason why the 2 thetas keep popping up. Okay? See, check this out. Let's talk about your go back to that stick of butter. Okay? Here's my stick of butter, right? Samurai sword. Let's cut like this, right? Now, let's take that cut and let's turn it 180 degrees. So cut, 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 cut. That's 90. That's 180, right? Is there really any difference on the stresses on that section whether I cut this way or I cut that way? It's still going through the section at the same orientation, right? Whether you cut downwards or cut upwards. So that's why you're seeing a lot of 2 thetas, because you remember, how do your trig functions behave? They always repeat every 360 degrees. Well, from our physics and from mechanics, the stresses are going to repeat every 180 degrees. Does that make sense? That's why you're going to see a lot of 2 thetas pop up in here. So that's all I got there. Now, how am I using these trig functions? Well, let's take sigma 1. I have p cosine theta divided by at, a over cosine. So I can flip my fractions and I get p over a times the cosine squared. So what's the cosine squared? The cosine squared is this. It's 1 plus the cosine of 2 theta over 2, right? What about the shear? I have negative p over a sine cosine. What's sine cosine? Negative sine of 2 theta over 2. Sound good? So, therefore, we can make the following statement. And this would sort of be like my big overarching statement that I want to get across to you, at least right now. So if I have a section that is seeing a stress P over A, or some stress, some sigma x, and I want to transform that sigma x into a stress on an inclined plane, sigma x can be transformed into sigma 1 and tau 1, 2 as follows. And this is sort of a big component of what we're talking about. Okay? So if an element is subjected to stress along the x-axis in an xy coordinate system, we'll generate new stresses along a 1, 2 coordinate system. Okay? Now I know that the notation and the trig is getting a little heavy, so I'm going to take my time with this and see if everybody's okay with what I got so far. Are there any questions? Let's see how we're doing on time. Oh, we're doing great. So far, so good? Now, everything that I've been doing for the past 20, 30 slides, I'm going to go back a few slides, everything that I've been doing for the past couple slides have all started with this, have all started with a stress along the x direction, okay? Now, if I'm starting with a stress along the x direction, I generate these stresses along 1 and 2. So that's with a stress in the x direction. Keep in mind that was only for stresses in the x direction. So I could do that whole derivation I just did, I could do it again for what happened if you have a stress in the y direction. Okay? If you have a stress in the y direction, you're going to generate different stresses, you know, maybe a sigma 2 or another tau 1, 2 or what have you, okay? If you do that, you will get what's called a different state of stress. Let's talk about state of stresses. Okay, so many structural elements and we could be talking about machines, we could be talking about beam columns and buildings, we can talk about whatever, it doesn't really matter. We could be talking about soil in the ground for you civil engineers. We could be talking about airplane wings for you mechanical engineers. We can talk about whatever. Many elements are subjected to loads that combine multiple different stresses in multiple different scenarios. Beams see it. I mean, we've already seen combined stress states just at beams. Any beam has, at any random point on the beam, a bending stress and a shear stress, right? Look at the shear and moment diagram. You can have a shear and a moment at a particular location. And if you have a shear and a moment at a particular location, you have two stresses at that particular location. So at that location, you can have what we call a state of stress, multiple stresses at one particular point. Now, if we investigate a differential element, and what I mean by that is if we take some random arbitrary structure and we look at a single random point on that structure. And when I say single random point, really what I'm talking about is an element on that structure that's itty bitty 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 wide this way and itty bitty bitty tall this way. Remember, like your dx's and little itty bitty tiny element. I propose that you can generate as many as 4 different stresses on that section. We can have a normal stress in the x direction. We can have a normal stress in the y direction. We can have shear stress in the y direction along the x plane, or a shear stress in the x direction along the y plane. So those 2 shear stresses. So we can have 2 normal shear components and 2 normal stress components and 2 shear stress components. Now this is in 2 dimensions. If you had 3 dimensions, you'd have 9. Like you could have normal stress this way, normal stress that way, normal stress this way, and you could have 6 different shear stresses. Okay? Now, combined at any random point on the structure, you could have a state of stress that looks like this. So what I really want to do is what I'm trying to figure out ultimately is here's my state of stress if I'm looking at it in this direction. What will my state of stress be if I rotated it a little bit? Okay, and that's really what we're after. Now, one thing that I sort of just like crept on you, and I kind of did this really quickly, is if you look on the previous slide, I have a tau xy and I have a tau yx. One thing that you can very easily derive is that those stresses are actually equal to one another. They are always equal for any state of stress anywhere. Okay? If you don't believe me, I actually have that derivation, and I have this even uploaded on Blackboard. So, if it'll load. I hope it loads. Okay, so let's say that you have a stress element, and I'm looking at this in 3 dimensions. So remember, we're talking about a little itty-bitty element in a structure. See, when we were looking at beams and axial loads and torsion, remember we would cut out a slice that's like itty-bitty, like dx wide. Remember that? Well, now I'm looking at a super tiny element that's dx wide, dy tall, and dz deep. Okay? Now, the area of each of these faces, so the area of this face is dx times dz. The area of this face is dy times dz. Okay? Now, why does that matter? Because if I look at this in 2 dimensions and I'm trying to look at forces, like what is force? It's stress times an area. So what is this y force? Well, it's the stress, sigma y, times the area. What is the area of this face? It's dx dz. Okay? What is the stress in the x direction, or the force in the x direction? Well, it's the stress in the x direction times the area, dy dz. Same thing from your shear stresses. The reason why this matters, if you sum moments at the center of the element, and then replace your forces with definitions for stresses, you find that your dx, dy, and dz cancel on both ends, and that your stresses are the same. See, one of the ways that we comment on stress, or one of the ways that we define stress states, is that stress states, we tend to refer to them as symmetric. In other words, that the shear stress this way is the same as the shear stress this way, and vice versa. So really, when we start doing these problems, like there are at most 4 stresses, but 2 of them are automatically equal. So when we start doing stress transformation problems, I'm only going to give you 3 stresses: a stress in the x direction, a stress in the y direction, and a shear stress. And that same shear stress is the same across the system. Now, like I said, what I have is I can define this stress state. I'm trying to determine what's that stress state. What would the state of stress be if we changed our orientation? Now, I had already derived these right here. I had already derived a sigma 1 and a sigma 2, or sigma 1 and a tau 1, 2. I could very easily do a similar derivation. So you're okay with how I got this and this, right? I spent like 20 slides doing that. I could do something very similar for this and this and this and this. I'm not going to subject you to that again because I've already done it once. At that point, it's just straight trig, okay? Everybody okay with this? If you're okay with this, what I'm going to do in the next couple slides is I'm going to collect all the like terms and see if I can see anything about it, okay? Excuse me. So if I start combining terms, okay, so what I'll do is I'll combine all the sigma 1 terms, all the tau 1, 2 terms, what have you, and I get this. So how did I get from this to this? I took all the sigma 1 terms, I combined them, and I factored it to make the math look at, to collect it into a smaller equation. How did I get the tau 1, 2 terms? Again, just add this, this, and this, and factor. That's all I got. And so that's how I got from here to here. Now you can very easily derive, so I only have a sigma 1 and a tau 1, 2. You could very easily derive the sigma 2 by replacing the angle with the angle plus 90 degrees and just redoing some of your math a little bit. Okay. All right. So I've got this. This box is really important. I would write this down. I'm actually going to let you write this down and give you a little bit of time on this. Oh, I'm sorry. I hit the button. So just to be clear, what is in this box is an incredibly powerful set of equations. If I have a state of stress defined about a particular coordinate system, I can determine what is another state of stress if I take that coordinate system and I rotate it. That's what's going on in this box right here. So, and this box right here, the name for this, if you need a name for it, is called stress transformation. Okay, that's what's in this box here, is what's called stress transformations. And if after writing this, you're going, man, Dr. Mike, who gives a damn about this? This just looks dumb. Why would you care about this? I'm going to show you a nifty little animation that I think will make it all make sense. And this animation, I think, describes it visually far better than I could do it verbally. But I'll try and add some commentary. Okay, everybody good? All right, now I'm going to skip this example for now. We're going to do this here in a second. Okay? All right, but I want to illustrate this. Okay? This is a bunch of trig functions, right? This is a bunch of trig functions, right? So would you agree that you could probably start plotting your trig functions and, starts looking something like this? We're going to get back to these trig functions here in a sec, but I'm going to show you this animation, then we're going to come back to it again. But I want to show you this video. This video illustrates what I want to describe far better than I could do verbally. So. Okay. All right. So let me explain sort of what we've got going on here on this this animation. So what we have is a state of stress that's originally defined as minus 120, 50, and 100. Okay? So we do some math. So let's say we have a member that's being yanked on and it's being twisted, right? So let's say you do your P over A and you find that it's experiencing 120 KSI in compression. And it's being twisted, so you find that your shear stress is 100 KSI in shear, okay? And that's this. And then you start asking the question, well, what happens if I take those section cuts and I start changing the angle, okay? Well, you agree based off what's in that box that if I have a state of stress like this and I cut it at a different angle, I'm going to get another state of stress, right? So what this animation did, this is actually a really brilliant animation. They started rotating the box at given angles, and for every angle computed a new shear stress. So watch this. Watch what's happening as you rotate the angle. See what's happening? The state of stress changes. Here, I'm going to turn the annotations off. See what's happening? The stresses are changing. Now let's just look at this. Let's just look at this state of stress. So this is a state of stress if the angle is like 96.9925 degrees. Okay? Look at your shear stress. Just look at the value. What is that? 117? What was it at the beginning? It was 100, right? So let's think about this from a design scenario. Okay? You do your math and you find that a shear stress is 100 KSI. So you size your shaft and go home and have a beer and call it a day. But you were determining those stresses based on the section cut like this. Well, what if the section cut was like this? I propose that if the section cut was like this at an angle of 97 degrees, the shear stress is larger, right? So your design may be fine if you're looking at the stresses this way. But what if the stresses are this way and the stresses are worse? You might think your section's going to be safe, but it might actually fail. Everybody okay with this? Now, I've got a couple other things I want to show you on this animation, but I'm going to sort of hold it to the chest for now. I'm going to sort of play this from pretty close to the chest. I want to go back to this example. Okay? I want to go to this example because I want to illustrate something on this. This is some really nifty stuff. Okay? Now, what I have here is I have a state of stress. Okay? I have that the stress in the x direction is positive 6 KSI, which, by the way, I've been sort of fast and loose on the sign convention. Any stress that is positive, like a normal stress, is a stress that's in tension. So look at the state of stress. See how in the x direction the stresses are positive because they're in tension? So look what we have for stress in the y direction. For stress in the y direction, we have negative 10 KSI. Why do we have negative 10 KSI? Because it's in compression. As for the shear, I have the shear as negative 5. And you can see the direction accordingly. I want to determine the stresses along a new coordinate system. And the stresses along the new coordinate system are if the axes are oriented as follows. Okay? So the first thing that we probably need to do is we probably need to determine what that angle is. Okay? All right, I'm going to minimize this. All right, so this is example 28. Now, I know the slides say 28A. We're going to go back to this example quite a bit, okay? So I'll go ahead and indicate that sigma x is 6 KSI, sigma y is minus 10 KSI, and tau xy is minus 5 KSI. One other thing about stress transformations, any of you who don't like units or not fans of unit manipulation, this is probably one of the easiest problems for unit manipulation because there are no unit manipulation. As long as everything is in KSI, your new stress state is going to be in KSI, so it makes it a little easier for you. All right. So part A, what we need to do is we need to find sigma 1, sigma 2, and tau 1, 2 at the following orientation. So we have a coordinate system that's sort of like that. So this is 1 and this is 2. And then we know that this is 3 and that's 4. So what we're looking for is that angle right there. So that angle, well, how are we going to figure that? Well, what's the tangent of that angle? 4/3. So the angle is the inverse tangent of 4/3. Somebody tell me what that is. 53.13 degrees. I have a second on that? Okay. All right. So here's what we've got. One other thing I'm going to go ahead and compute is 2 theta, because we are going to use 2 theta quite a bit. So 2 theta, that's going to be, what, 106.26? All right. So here's my state of stress. Now let's compute a new state of stress. So we need a sigma 1, a sigma 2, and a tau 1, 2. Now how do we compute these? Well, we go to the box. We take sigma x plus sigma y over 2 plus sigma x minus sigma y over 2. And then we multiply that times the cosine of 2 theta. So now you can see why I threw the 2 theta in there, because there's going to be a lot of those. And then plus tau xy sine of 2 theta. Now, instead of plugging and chugging all the ways, why don't you all tell me what that is? I want you all to do that. I want you to plug and chug and tell me what sigma 1 is going to be. And I almost just want you to do that because I know the equation's a little involved. So I'd almost like to see you practice it out to make sure that you're comfortable using it. Anybody have a sigma 1 for me? Negative 9.03. Do I have a second on that? Uh-oh. 3, oh, so it is 4. Yeah, no, leave it negative because it is in compression. It is in compression. So sigma x was 6 KSI in tension. The sign matters, okay? And from a material standpoint, the sign can matter a lot. Like, for instance, in concretes for you civil engineers, or for ceramics for you mechanical engineers, those materials tend to operate very well in compression but very poorly in tension. So that actually does matter. So shear is usually, I mean, you need to maintain your sign for appropriate transformation, but from a mechanics perspective, if there's any one stress where the sign matters the least, shear. I'm not saying it doesn't matter. I'm just saying it usually matters the least. So, everybody okay? All right, so here's sigma 2. So the formula is very simple. So if you can go into your calculator and, just like change the signs from your previous calculation. What do we got for this one? And so really the ones that changed are that sign. And so those are your signs that changed. Anybody have a value? You said 2.64. I feel like, no, that's fine. 504. Okay, all right, 504. So just so we're clear, remember we have a new stress block that's like this, like at a new orientation. So what we're getting, just so you are aware from the mechanics, this is 9.04. That's 9.04 in compression because it's pushing on it. And this one is 5.04 and it's yanking on it. And all these stresses are in KSI. So I'll put stresses in KSI. Okay, now for shears are, the formula is a little different, minus sigma x, minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cosine 2 theta. Move this up some. Negative 6.28. Have a second on that? All right. So since that's negative, so we're gonna say that. So that would be our new state of stress with the element being rotated. Is everybody okay with that? Any questions? All right. Now, I want to show you something. All right. I want to show you something. I want you to take a look at this. Okay? Now, would you all agree there's a bunch of trig going on? So what I have in this plot should not be the craziest thing you've ever seen, right? Those are stress transformations as a function of the angle. So let's take the normal 1, 1. Okay? What did you get for sigma 1? What did you get? What was the value? Remind me. Negative 9.04. So look right here, right there. Look what we've got. What's the angle? The x-axis is the angle, and what is that angle? Maybe about 53.13 degrees, right? What's the stress? 9.04. What is more interesting is, what is that stress if the angle is 0? What's that value right there? It's 6, right? What was the original stress state? 6 minus 10 minus 5. How about 6 minus 10 minus 5? And then as those stresses rotate, we get higher stresses, right? That makes sense? Not too bad, right? Cool stuff, isn't it? Now, so this came out to be, what was it, minus 9.04. What is this value? Maybe it's positive 5.04. What is this value? I don't know, maybe it's minus 6.28. Crazy, isn't it? Really cool stuff, right? Any questions? So what you're seeing in this plot is the orientation, or how the orientation affects your stresses, okay? So if I go back to that video I showed you, it's basically just the same thing. As your angle changes, your stress state goes from one to the other, right? Now, would you also agree that certain stresses get larger and certain stresses get smaller depending upon what angle cut you make? Like, you might get different stresses at 20 degrees than you would 40 degrees, and one might be the worse than the other, right? So maybe the worst, what we really want to determine is, what's the worst case scenario overall? What is the absolute worst case scenario stress state for design purposes? That's what we really want to find out. Well, this graph has some really, really nifty components to it if you really take a look at it. Now look at this line that I've drawn, okay? That line is really, really nifty. Let me go back to this. I have this graph drawn in a very particular way. The solid lines, the solid curves, are the normal stresses. The dashed lines are the shear stresses, okay? Would you agree that right here and right here are where the maximum normal stresses are? Like, those are your plateaus. Same here and here. But look what happens at those locations. What's your shear stress equal? 0. That's a really interesting point. See, look at this. Same thing happens over here, okay? Where you have 0 shear stress, you have maximum normal stress. And where your normal stresses equal one another is where your shear stress is maximized. Everybody see that? There is a way that we are going to express this graphically, okay? And the way that we are going to express it graphically later is, we're going to graph normal stresses on this axis. We're going to graph tau stresses, shear stresses, on this axis. And what we're going to find is that plot kind of looks like a circle. And there's a name for that circle, and we call it Moore's circle, okay? I'm going to leave that part there because I don't want to ruin that. But let me explain where this is headed. So here's where this is headed. When you plot that out, you find that maximum normal stresses are where shear stresses equal 0, okay? So what we're going to do next time is we're going to take this state of stress and we're going to try and define two things. Number one, we're going to try and define what is the maximum shear stress overall. The second thing that we're going to define are what are called principal stresses. Principal stresses are these stresses here and here. We're talking about that stress and that stress. What is the absolute maximum normal stress? Because as a designer, that's what you care about. That's what you need for the purposes of design, and we call those principal stresses. We're then going to take a look at stress transformations, principal stresses, and all this stuff and ask ourselves, this math is really funky and it's really complicated. Is there a way that we can make it simpler? The answer is yes, through an analytical tool called Moore's Circle. So it all is kind of the same topic, okay? So this is really where mechanics of materials comes together. This is where all the individual topics that we handled, way back when, axial loads, and torsions, and beams, and all that crap. This is where it all comes together, and we really start applying some real complex engineering to the system. I'm actually going to stop it there. That's all I have for you today. Don't forget your homework, due on Tuesday. Your exam grades are posted. I'll get attendance grades updated by the end of business today. Homework's due Tuesday again. Y'all have a wonderful weekend. I will see you on Tuesday.